All right, welcome. Today, we are going to tackle a really cool technique that can take your code from agonizingly slow to basically instant. If you've ever found yourself stuck with a huge chunk of data and just tons of repetitive questions about it, then you're going to love this. So, picture this. You've got this massive list, maybe 100,000 numbers long. And then the questions start flying in. Hey, what's the sum of all the numbers from index 200 all the way to 50,000? And then, okay, now what about from 10 to 90,000? If your gut reaction is to just loop through and add them up every single time, well, you're headed for a world of hurt. Okay, let's make this real with a simple example. So here we've got an array RR equals 241736. It's small, it's manageable, and the queries start coming. What's the sum from index 1 to 4? Or how about from index 2 to 5? So how would you even start to solve this? Well, let's look at the most obvious way first. Now, this first method, we call it the brute force approach. And it's called that for a reason. It's direct, it makes sense, but it's a trap that seems totally fine when things are small, but fails spectacularly when you try to scale it up. And the code for this? It's super straightforward, right? You make a function, it takes the left and right spots, L and R, you start a sum at 0, and then you just loop, a simple for loop. For int I equals L, I is less than or equal to R, I++. And inside, all you're doing is adding the number at each spot to your total. Sum plus equals R of I. I mean, it works. For our little array, it's perfect. But what happens when the numbers get big? This is where the trap snaps shut. Let's go back to our big problem. 100,000 elements, 100,000 queries. The total number of operations just explodes to 10 billion. That's a 1 with 10 zeros. No computer, I don't care how fast it is going to get through that quickly. Your program is going to freeze, it's going to time out, it's a total failure. So, brute force, it's a dead end. But what if I told you there's a way to answer any of these questions, not in millions of steps, but in a single operation? What if you could make every single query instant? And this is where we pull out our secret weapon, the prefix sum array. This is the whole key. It's the technique that turns this impossibly slow problem into one that's laughably easy. And it's all about thinking ahead. So what is a prefix sum array? It sounds fancy, but the idea is actually super simple. All it is a new array that we build, just once, from our original one. And at each spot, instead of storing the original number, we store the running total, the cumulative sum of all the numbers from the very beginning up to that point. Let's actually see this happen. So on the left, there's our original array again, 2, 4, 1, 7, 3, 6. Now, let's build a prefix sum array on the right. The first number is 2, so our first prefix sum is also 2. Easy. Now, for the next spot, we take our last sum, which was 2, and add the next original number, 4. So 2 plus 4 is 6. That's our next value. Now we take that 6, add the next number, 1, and we get 7. Take the 7, add the next number, which is also 7, we get 14. Keep going. 14 plus 3 is 17. And finally, 17 plus 6 is 23. And boom, we're done. Our new array is 2, 6, 7, 14, 17, 23. And this gets to the very heart of the strategy, what we call pre-processing. The whole philosophy here is to do a little bit of extra work up front, just one time, to build this new, smarter data structure. And why would we do that? Because once we have it, all those thousands of queries that were so slow before become almost magically fast.
And the code to build this thing? It's ridiculously efficient. First, we just handle the first element, prefix 0 equals R0. Then we just loop through the rest of the array one time. 4 and I equals 1, I less than n, I++. And the logic inside is so simple. The prefix sum at any new spot I is just the prefix sum from the spot right before it, prefix I minus 1, plus the current number from the original array, Ri. That's it. We just walk down the line once. This is what we call an O of n operation. The time it takes is directly tied to the size of the array, and we only have to pay that cost once.
Okay, so we did our one-time prep work. We built our fancy new prefix sum array. Now, for the payoff. Let's see how this thing gives us the answer to any query in what we call constant time, or O of 1, which really just means it's instant. It takes the same tiny amount of time, whether the range is 2 numbers long or a million. The formula is just beautiful. To get the sum of any range from L to R, all you have to do is this.
You grab the pre-calculated sum all the way up to r, which is just prefix r. Then you grab the pre-calculated sum of everything before your starting point, which is prefix l-1, and you just subtract them. One number minus another number, one subtraction. That's it. You've got your answer. And if you're wondering why that works, think of it like a cake. The prefix sum array is like the whole cake, right? Prefix r represents the value of the entire cake from the very beginning up to slice r. But you don't want the whole thing. You only want the slice from L to R. So what do? You just cut off and remove the piece you don't want, which is everything from the beginning up to slice L-1. And what are you left with? Exactly the piece you were asked for. So let's just put these two methods side by side. The difference is staggering. Brute force has 0 prep time, but each query is slow, O of n, giving us that disastrous O of n times q complexity. Our prefix sum method has a tiny one-time O of n cost upfront, but then every single query is O of 1, instant. So our total is O n plus q. For our big problem, that's the difference between 10 billion operations and maybe 200,000. It's a complete game changer. And this whole idea has a name, a really important one in computer science, the space-time trade-off. It's this core concept where we knowingly use a bit more memory, a little more space, to create our prefix sum array. And in exchange, we get a massive, massive reduction in the time it takes for our program to run. It's a trade we make all the time to write better, faster code. So we've totally mastered this for a single line of numbers, right? A 1D array. But what if our data isn't a line? What if it's a grid? Like a spreadsheet or the pixels in an image? Well, let's level this up because this powerful idea extends beautifully to 2 dimensions. Okay, for a 2D grid, the idea is exactly the same. We just have to think in rectangles instead of lines. Every single cell in our new prefix sum grid is going to store the sum of the entire rectangle from the top left corner, 0, 0, all the way down to that cell. Now, don't let this formula scare you. Prefix ij equals matrix ij plus prefix I minus 1j plus prefix ij minus 1 minus prefix I minus 1j minus 1. All it's doing is some simple accounting. To get the sum for the current cell, we take its value, add the entire rectangle of sums above it, add the entire rectangle of sums to the left of it, but wait, now we've double counted the top left corner rectangle, right? So we just have to subtract it out once. That's all it is. And querying for a subrectangle? You guessed it, it's the same idea again. This formula might look like a beast, but it's just our cake analogy with more dimensions. To get the sum of the little rectangle you want, you take the big pre-calculated rectangle that goes all the way to its bottom right corner. Then you subtract the 2 big chunks you don't want, the area above it and the area to its left. But just like before, you've now subtracted their overlapping corner twice, so you just have to add that little corner back in once. It's just a few simple additions and subtractions to perfectly carve out the exact area you need. And look, this isn't just some abstract puzzle for interviews, okay? This is a real-world tool. It's used all over the place in image processing to instantly calculate things on a block of pixels. It's used in game development to figure out what's happening in an area on a map. And yes, it comes up all the time in technical interviews because it proves you can think past the obvious slow solution and find something truly efficient. So here's the big takeaway. The prefix sum is more than just one algorithm. It's a mindset. It's about training your brain to spot repetitive, slow work inside your loops and to ask that crucial question, wait a minute, can I do some work up front just once to make all of this faster? So I'll leave you with that to think about. Where in your own code, in your own projects, is there a slow loop just waiting for you to speed it up with this idea of pre-processing?